Most directions turn. 1 refuses. Watch 9 arrows move at once. 8 change direction. The yellow one does not. It stretches, but it never leaves its original line. Apply the same matrix again. The yellow arrow still stays on that line. This is not a lucky arrow length. Every non-zero arrow on that line follows the same rule. That special line is an eigendirection. An arrow on it is an eigenvector. Now let us find out why. Instead of guessing an eigenvector, rotate one probe arrow slowly through every possible direction. For each angle, compare the original arrow with its transformed image under the matrix. Usually the two arrows disagree. The transformed arrow points somewhere else, so the turn error is positive. But near the diagonal the error shrinks. The two directions are getting closer and closer to alignment. At exactly 45 degrees, the error reaches 0. The matrix changes length, but creates no turn at all. Rotate another 90 degrees, and the error reaches 0 again. This matrix has two eigendirections. Now freeze the yellow direction and watch what the matrix actually does to one vector on that line. The vector starts at one copy of the direction and ends 3 times as long on the very same line. Doing the full matrix transformation gave exactly the same endpoint as simply multiplying by 3. That is what the equation mv equals lambda v means. Matrix action becomes ordinary scaling on this direction. The vector v is the eigenvector, and lambda is the eigenvalue. Here lambda is 3. The important part is not the symbol. It is that a complicated two-dimensional map becomes one-dimensional scaling. An eigenvalue does more than tell you how much the arrow grows. Its sign tells you which way it comes out. With lambda equal 2, the arrow doubles and keeps pointing forward along the same line. With lambda equal 1/2, it shrinks to half its length but still keeps the same direction. With lambda equal -1, the arrow stays on the line but flips to point the opposite way. And with lambda equals 0, the whole eigendirection collapses to the origin. That information is destroyed. So one number describes stretch, shrink, flip, or collapse along a direction the matrix never bends away from. Eigenvectors become especially useful when the same matrix is applied again and again. Start with an ordinary vector. It can be split into pieces along the two eigendirections of this matrix. One piece is multiplied by 3 each step, while the other piece is multiplied by 1. After one step, the faster component is larger. After 2 steps, it dominates the picture even more. After several steps, the whole vector points almost along the eigenvector with a larger eigenvalue. That is why eigendirections appear in repeated dynamics. They are the directions the transformation amplifies predictably. There is one final connection, and it points directly to the next episode about inverse matrices. If a matrix stretches this eigenvector by 3, a perfect rewind must shrink that same direction by 1/3. The eigendirection stays the same. The inverse simply replaces the eigenvalue lambda with 1 over lambda. That works for every non-zero eigenvalue, because a non-zero stretch can always be undone by the reciprocal stretch. But an eigenvalue of 0 has no reciprocal. Once a whole direction is crushed to 0, there is nothing to rewind. So next we can ask the geometric question behind an inverse. When can every point in space find its unique way home?